Okay, so good evening, everyone. I am Prachi Pasalkar. I am Program Manager at Pune Knowledge Cluster. On behalf of Pune Knowledge Cluster, I welcome all our participants for the first session of this course. So just few things about Pune Knowledge Cluster. Pune Knowledge Cluster is an organization set up by Principal Scientific Advisors Office, Government of India, and it is one of the 6 science and technology clusters in the country. PKC is administered by IUCAA Pune, the Inter-University Center for Astronomy and Astrophysics Pune. And the objective of Pune Knowledge Cluster is to get together industries, research institutes, educational institutes, citizens to one platform and try to find solutions to the problems that are related to the city, try to find research-based innovative solutions to the problems and related to the city, and also scale it up to the national level. So we have various focus areas or verticals on which we work. That includes health, environment and sustainability, sustainable mobility, big data, AI, and capacity building. So under the umbrella of capacity building, we do various activities for students, teachers, working professionals, citizens, etc. These includes high-end courses like this one, the Exoplanet course, like the one that you have signed for, seminars, webinars, citizen science activities. So if you're more interested in knowing about what PKC does, please visit our website and our social media handles for more details. So this particular course that we are holding under the capacity building vertical, this course includes 14 sessions starting from today. So starting from today till 28th of February, we will be having courses. The schedule is already shared with all our participants. I'm happy to mention that we have participants from different parts of the country and also different parts of the world. So that is a good thing we have. And I now request Professor Ajit Kembhavi to say a few words. Professor Kembhavi is the principal investigator of Pune Knowledge Cluster, and he is a renowned astrophysicist of the country and former director of IUCAA Pune. Over to you, sir.
Thank you very much, Prachi. So I'm very happy to welcome all of you to this course, which Dr. Ravi Koparapu of NASA and I are together curating. Now, as far as I know, this is probably the first course on exoplanets being offered in the country. And we thought that we should have a series of lectures by experts on the matter. So, like Pachi said, the Pune Knowledge Cluster organizes all sorts of courses. And there could be courses on molecular plant breeding, or there could be a course on AI for cybersecurity and so on. And so this is the first astronomy course that we are organizing. And it is intended not as a pure astronomy course, but as an interdisciplinary course. Because as the lectures develop, so you will find that there are many, many things which go into the understanding of exoplanets, which is the same as trying to understand our planets. So if you want to understand our planets, pure astronomy will not do. So because there are all kinds of atmospheric science, and there's geoscience, and there's all sorts of things coming in. With the exoplanets, the problem is that they are so far away. So we have difficult enough, it's difficult enough for us to actually study even close by planets like Jupiter, large planets like Jupiter, Mercury, Mars. And only now we have got probes going to them and which have been detecting them in situ. Exoplanets are very far away and you can barely resolve them. Okay, meaning that you can get a direct image of an exoplanet in very special circumstances, just for a few of those. And mostly the planets cannot be resolved from the stars. Nevertheless, we have made great progress in detecting them, finding them, detecting them, making measurements and understanding them. And that is what this course is going to be all about. So the first 3 lectures, the first 2 are by me on stars. I'm not going to tell you anything about planets at all, but there are certain facts about stars that you will need during this course. And so the idea was to have a 2-lecture course on stars. And then Dr. Ravi will join me after I finish these 2 lectures. He will give an introductory lecture on exoplanets, about how to detect exoplanets. So after that, there'll be a number of people coming in who are all specialists from India as well as from abroad, and who will talk about specific aspects of exoplanetary physics. And then we intend to have a series of seminars by experts again all over the world, And those will go on. Maybe we'll have 6 or 8 seminars, and after that, from periodically, depending upon how much interest you people have, we could later have a more advanced course, or we could have a actually face-to-face workshop. So the possibilities are many, many, and they all depend upon the kind of response that we get from people like you. So thank you very much. I request Ravi to say a few words now, after which I'll begin my lecture.
All right. Thank you, Dr. Kembhavi. And of course, thank you, Prachi, for arranging this course. So my name is Ravi Kopparapu. I'm a planetary scientist at NASA Goddard Space Flight Center in US. I studied here my master's in Pune University, and I did a project with Dr. Kembhavi 25 years ago. And so he's my mentor. So I'm so glad to, very glad and very happy to organize this exoplanet course with him. And so one of the things that you may have seen in the last few years, if you have been reading the news, is this news about how scientists have found a planet here around near to our stars or near our solar system, or finding life on other planets. And most of the time in the last couple of decades, the finding life on planets has been focused on Mars, or one of the nearest planets to Earth. And that is a nice thing to do because it's the closest one. We can send probes, we have that luxury and all, like Dr. Kembhavi mentioned. But over the last 30 years, exoplanets, we suspected there were exoplanets, but now we have found many, many thousands of them. And the goal of this course is to give a brief introduction to how these exoplanets were discovered, what are they actually, how do they look like, what kind of atmospheres they have, and what is the current status of finding life, alien life on those planets. And so my hope is, after we are done with this course, when you read a news article and when you read that, oh, the news says something about the nature of the exoplanet, you would be able to clearly understand then, oh yeah, I read that about that in the course, so I can clearly understand a little bit more about the exoplanet. And so this is a real world connection that you can have, that the more you understand about this, the physics and also the nature of exoplanets, the more you understand about our own world and how fragile we are living on this planet. And that gives you a perspective about how we can interact with the world around us. As Dr. Kembhavi said, I'll be talking about the history of exoplanets on Friday, and I'll give a brief introduction about the detection techniques, how they were able to detect, and why was it so difficult to detect exoplanets until now, and why are we starting to detect them right now. And there are other speakers who will talk more about that. With that, I'll ask Dr. Kembhavi to begin the course, and we'll talk about stars, and then we'll go from there.
Thank you, Dr. Ravi. So just before Kembhavi sir starts projecting his screen, few instructions for the participants that if you have questions, please type it in the chat box. We will get to it at the end of the session. And with me, I have my colleague Gayatri Shivsagar, who is also coordinating, who will be there for the entire course. So yeah, hi Gayatri. Okay, so just start putting your questions as in it comes to you in the chat box. We'll take it at the end. Thanks.
All right, I have to share my screen now.
We can see your screen.
One moment.
Yes.
Right, you can see the whole screen now?
Yes, in the full screen mode, yeah.
Okay, all right. So thank you very much, Prachi. And there are several things that I'm going to talk to you about today. Now, whatever I'm going to say today and tomorrow, it's a 2-lecture thing, Introduction to Stars, Stellar Astronomy and Astrophysics. And I can give you this introduction either as 2 lectures, or about 4 or 5 lectures, or 40 lectures. Right. So clearly, a different detail will be covered depending upon the extent of the course. So I'm going to be very brief here. I'm going to introduce various ideas and leave them there. So what we will do is that as I pass from one set of ideas to another, one set of related ideas to another, then I'll ask for questions rather than leaving all the questions to the end. And it is extremely important for you to make this course participatory. Okay, in the sense that please do ask questions, and you can possibly even discuss things with each other later, and Prachi can set something up for you. And if there is enough interest, we can also have a block thing, etc. So let's make it interactive. It will be totally wonderful to have such a course face to face, but we'll do that in the future. Right. So here is the most important star for us, which is the sun, and you will see the sun red like this mainly during the sunset and sunrise because of the dust. So you can see the sunspots there, which were first seen by Galileo about 1612. That's quite long ago. So the sun is a completely average star. Neither too big nor too small, neither too hot nor too cold. And then it has got a radius of about 7 into 10 to the 5 kilometers. Okay, which is the radius of the sun, and it is at a distance of 150 million kilometers from us. 1.5 into 10 to the 8 kilometers. So it has got a luminosity, meaning that the amount of energy that the sun emits is 4 into 10 to the 33 ergs per second. Okay, and then the amount of energy and the mass of the sun is 2 into 10 to the 33 grams. So I know that you people are more familiar with MKS units, but these numbers are stuck in my mind, so I don't want to have confusion. Right, so these are elementary facts about the sun, and the fact that it is typically yellowish in color tells you what is the temperature, because you can simply apply the black body laws, and I'll come to those during the course of my lectures, and then it tells you that the temperature of the sun is about 6,000 Kelvin, and there's a more exact number known. But when you say that there is a temperature of the sun, it means that it is the temperature at the surface of the sun. So the radiation that we are actually seeing from the sun just comes barely from 50 kilometers below the surface. And you must understand that the surface is not very well defined. Meaning that the surface of the earth is uneven, but it is pretty well defined. Whereas because the sun is a ball of gas, so we know that it is made up of hydrogen and helium and small fractions of heavier elements. So it's very hot and it is gaseous in nature. Okay, so which would mean that it has no hard boundary, but there are technical ways in which one can define a boundary, and then you can also say that the radiation that you see comes from about 50 kilometers, but the energy is produced very deep inside. Now, if you can put different filters so that you see wavelength of light coming from the sun through these filters, and then you get different appearances of it. So here you can see a very large flame coming out. So if the radius of the sun is 7 into 10 to the 5 kilometers, then this must also be very large in size. Okay, so these are things coming out because of the interaction between the hot gas and the magnetic field and so forth. And then you see this nice image of the sun. All of you will recognize it's an image taken during the total solar eclipse. Right, so you can see here what's called the corona of the sun. And the idea is that the temperature at the surface is about 6,000 Kelvin, as I told you. And as you go inside, the temperature, it keeps increasing until it's about 15 million Kelvin at the center of the sun. So as you move outwards, the temperature constantly decreases. But then you come to a point beyond which the temperature increases because of specific processes which are taking place there. And then you see the blue color of the corona. This is yellowish color, this is blue color, so this is clearly at much higher temperature. But you can get even much higher photons than blue color photons from it, like the X-ray photons and so forth. Right, and so this is again a very nice picture of the sun. So which shows the highly resolved magnetic field lines, and there are charged particles which are moving along the lines trapped in the magnetic field and which are emitting radiation. So you have got extremely detailed pictures of the sun now because it is very close by, and then you can get high resolution images of it. So we know that I know that you people all come from slightly different backgrounds, but I trust that I'm going to be using simple physics, and I trust that you people know it. But if you have any real difficulty, then when you can ask me during the question time, and then we'll try to solve those. Right, and so here is a close-up of the sunspots. I'm showing this to you just to say that how active is the surface of the sun. And the fact that the sunspots are dark means that they have got a lower temperature than the rest of the sun. And then here on the surface, you can see the granularity. Right, so this is the kind of thing which you get from high temperature, the high resolution imagery using different techniques. And in contrast to that, so this is sunspots, a picture of the sunspots made by Galileo, who was observing the sun with a small telescope. Okay, so the sunspots are amongst the great discovery that Galileo made. And this is the original sketch made by him. Right. So now when we talk about stellar physics, and we could be talking about the physics of a star like the sun, but we'll see what kind of wide variety of stars is possible, so that the details of the physics can be quite different from star to star. But what you have here, I have put down the main things which you have to take into account. So first of all, we have got hydrostatic equilibrium. So what does one mean by that hydrostatic equilibrium? Is that you see the sun has got more or less fixed size, and that size has remained fixed for millions of years. And so therefore, it must be in some kind of a mechanical equilibrium, because otherwise, if it is not in equilibrium, then it would go on expanding either slowly or very rapidly, or it could contract and collapse. All of those things happen at different stages of the life of a star. But in what is now called the main part of the life, which is called when it is on the main sequence, and I'll tell you the meaning of that quite soon. Okay, then you say that the sun is in hydrostatic equilibrium. So what is that equilibrium due to, and what are the forces which are maintaining the equilibrium, we'll come to. Then you need to, the sun is constantly emitting energy. It's emitting energy at 4 into 10 to the 33 ergs per second, as I told you. That's roughly what's called the bolometric luminosity, means the total energy which is emitted by the sun. And so this energy is coming to the surface, but it is traveling from the center of the sun to the surface. And you need the theory of how the energy is transported. Then you can transport the energy, but where did the energy come from? So that energy must be generated down the center. And there are people speculated on different mechanisms, but now we know that it is due to nucleosynthesis. So which means that at the center, due to the process of nuclear fusion, hydrogen is getting converted to helium, right? And then helium can get converted to heavier elements. And that process is known as nucleosynthesis. So when you put together all these three properties of the sun, and then also you need the properties of the matter which makes up the sun. We know that it is in the form of a gas, but what are its properties? What is the density of the gas? What is the temperature of the gas? What is the pressure of the gas? Okay, and what is the equation of state of the gas? So when you take these equations of energy generation, energy transport, and hydrostatic equilibrium, and then you have the properties of the gases which make up the sun, then you'll see that you have got enough equations to actually obtain the theory of the sun. Okay, meaning that you have the differential equations, and then you have got the equations of state, etc., the properties of matter, and then you can solve it all to get an idea of the structure of the sun and its evolution, because energy is being produced in the sun, and however large the size of the star is, it should be that there must be a finite source of energy. So the question is, does that finite source of energy, when would that source of energy be exhausted? And when that is exhausted, how will the star change? Okay, so which would be the theory of stellar evolution. And then we will see that the process of evolution goes on two tracks. One track is that there are stellar explosions. Okay, they can be a planetary nebula or they can be a supernova, right? And then as the star, when it reaches certain evolutionary stages, it will explode. And as the outer layers get thrown out, the inner layers collapse and they form a compact object. Okay, that object is, it could either be a white dwarf, or it could be a neutron star, or it could be a black hole. Right. So, so this is the story of stars, which we are going to develop over the next today and tomorrow. Then one question that you may ask is, are the stars always lone? I mean, the sun appears to be just a single star there. Are stars always single, or can they also appear in more complex configurations? Then it turns out that a very large fraction of the stars are in binary systems. Okay, binary systems meaning that these two stars, there are two stars which are gravitationally bound together and then which go around each other because they're bound. And a bound system, and it will remain bound for a very, very long time. And there are situations in which one of the stars can explode and then the system changes, the system can disrupt because of the explosion. Otherwise, it remains stable for a long, long time. Then, just like there are two stars in the binary, there can be sets of three stars, right? So, but it typically turns out that when you've got, it's very easy. You can get a beautiful two-body problem solution of a binary star. But if there are three stars there, then you will not be able to get a proper solution. In fact, these systems are, in the long term, just unstable. But on the other hand, you could go on adding more stars to it, to the system, and you will find that there are systems. Some of you may have seen the Pleiades constellation, where there are about close to 80 stars, I believe, out of which you can see 7, 8, 9, 10 stars, depending upon how good is your eyesight. And so this Pleiades, which is known as Kritika. And then, but you can keep increasing stars in these groupings, and then when you really go to the limit, you get what are known as globular clusters. So globular clusters can have 500,000 stars in them, and these globular clusters are gravitationally bound. Okay, meaning that these stars, the gravitational force of the stars taken together is enough to make it a bound structure. So just like our sun and the planets around the sun, the 8 planets and lots of other objects, they together form the solar system. And these objects are all, most of them are bound to the sun. Okay, so when you have a very large number of stars, then their self-gravity can be sufficiently high so that it becomes a bound system. So we are not going to go beyond binary stars here in this one. But the other thing, the dynamics of the other is also extremely interesting. So here is that you have got the inner part of the sun, right? I mean, you are looking inside. It is impossible for us to look inside the sun, we go beyond 50 kilometers or so, and that is because the radiation is the rest of the sun is opaque to the radiation which comes from the inside. So if it is opaque, then how does the radiation finally manage to reach the surface and leave the star? So that is a very interesting story which we'll come to very briefly. And so you start with the surface of the sun as we see it, and then this is called a photosphere because there's a light emitting part. We see the light emitting by the photosphere, and then it is not as if the sun is a boring object just sitting quietly there. There are all kinds of subsurface flows and things and gas. It's a very dynamic object. There's convection which is taking place in it, and the magnetic fields which confines the matter to move in a certain way. Okay, and then when you at the innermost part of the sun is that you have got what is known as the inner core, and the temperature in the inner core is sufficiently high for hydrogen to be converted to helium. So the core will consist of some helium which is already produced, or the 4.5 billion years or so of the lifetime of the sun, current lifetime, and then current age of the sun, and then you have got then there will be other different layers, and now there are layers which are called radiative zones, in which energy is transported. Energy is transported by radiation, by the passage of photons through the sun. Then you have got the convective zones. You can see there's a convective zone here, the convection zone, and there can be a convection zone inside also. Okay, so there the energy is transported by convection. So when I was in high school, I was told that there are three methods of transporting energy. Okay, one was conduction. Okay, and then the other one was convection, and the third one was radiation. And I was completely confused by what I was told about them, and I found that the whole business incredibly boring. Okay, because when you're conduction, then we also had an experiment on conduction where you heat a bar at one end and see how the temperature changes along the bar, and so we are told that their energy is being transported by conduction, and those experiments never worked. Okay, then there was convection. So they say that you see the bubbles coming out when you boil water, and that is convection, and that seems to be even more boring. Okay, and then there is radiation, which are too difficult to understand. Okay, so energy transport consisted of these three thoughts, right? So, but now as you go deeper and look at it, the whole thing is incredibly interesting, and then there's incredible union of physics there, because conduction and radiation are because of transport. Conduction is because of the transport of electrons, and radiation is because of the transport of photons. And it turns out that exactly the same differential equations are in action when energy being transported by conduction or by radiation. Convection, it turns out, actually involves macroscopic flow of fluids and transport of fluids from one part to the other. The physics is very interesting, but it is incredibly difficult. Okay, because you've got what the effect of turbulence, and it is a turbulence which makes which is difficult to study, and it is a great unknown in stellar astrophysics. All right. So now, before I go further, I want to introduce some concepts to you. Right. So they're very simple concepts called flux and luminosity. So so let us suppose that you have got an object, let's say the sun, with a luminosity L. So what is luminosity? It is the amount of energy which is emitted by a star per second. So the star is very far away from us. So for all practical purposes, we can say that it's a point source of energy which is emitting L ergs per second in whatever energy, L energy units per unit of time. Then now if I measure if I'm at a distance d from this object, then the flux, which is the amount of energy which is received per unit area of a surface per unit time, would be L upon 4 pi d square. Right? Because it's easier to understand the other way around also. If F is the amount of energy which is emitted is received per unit area, per unit time at a distance d. Now, you can imagine when I'm at a distance d, it is as if I'm part of a surface whose area is 4 pi d square. And this energy, F is energy per unit area per unit time. So the total energy per unit time will be L is equal to F into 4 pi d square. And therefore I get this, equation. Okay, so then what are the numbers per sun? I typed this in just about 5 seconds before 4:30. So I made a mistake here. This should be 4 into 10 to the 33 ergs per second. I already said that. Okay, which is the luminosity of the sun, and the distance is 1.5 million kilometers. So which translates to 1.5 10 to the 13 centimeters. So the amount of energy which is received from the sun is, as I told you, it should be more than this 1.4 because the factor of 2 was missing into 10 to the 6 Earth per second per centimeter square per second. So which are the flux, right? So the total amount of energy emitted by the sun is totally enormous, and we are so far from it, and yet we get this kind of energy uh, emitted for this. And this energy is the basis of all life on Earth. Okay, so without the energy coming from the sun, there'll be absolutely nothing, and we'll just be very cold at a temperature of interstellar space, and there will be nothing much happening on the Earth. Right. So now these are all large numbers, and then it is extremely difficult to make absolute measurements, meaning how much energy I'm actually getting per area, per unit time. And also when I say energy is at what band of the electromagnetic spectrum. So is it, so it turns out that you don't really make this kind of bolometric measurements at all. What you do is that you take certain filters like red filter, blue filter, green filter, and so on, or in the infrared, near infrared, ultraviolet, and then all these filters in a certain band which is relatively narrow, you see what is the energy which is coming through. And therefore, now it turns out that you require modern instruments to make these absolute measurements which give these numbers. But people started looking at stars millennia ago, and in every country, right? In Egypt, in Greece, in things, and in India, people did astronomy, and then they observed stars. You can observe about 4,000 stars on a clear night. And no, 4,000 should be the total number of stars that you can see around us with the naked eye generally. And so at any given moment, you see half the sky, so you see about 2,000 stars. Okay, so ancient astronomers determined the positions of these pretty accurately. They determined the positions so accurately that they could discover the phenomenon of what is known as precession of the equinoxes. Okay, meaning that the Earth's axis is precessing in the sky at a very slow rate. Okay, and so that was, they did not know what the phenomenon was, but they could see what difference it made to the positions of the stars. So similarly, it was necessary to actually discover the what are the flux, what the energy being received from a star. So rather than make absolute measurements, which are not possible at the time, so people compared stars. Okay, so the method that we follow here, as I said, that these are independently in very different countries, but here we are using the formulation from Greece, let's say. So now it turns out that the response of our eye to radiation is logarithmic. Okay, so what does that mean? You see that we can see flux on a tremendous range, many orders of magnitude, and so clearly you can't have a detector which can detect linearly over those when there are thousands and thousands of units involved. So the response of our eye is logarithmic. And then I would strongly advise you to read this up a little bit. So what astronomers have done, I mean, using precepts which came to us from ancient times, so we define a quantity which is called the magnitude, which is equal to minus 2.5 log of the flux plus a constant. So see, if you can take a log only of a dimensionless quantity, but then you have done that by, you have adjusted those units by taking the constant here. And the constant will depend upon which units you are using to make these measurements and so on. Okay, so this is called the magnitude. So you see that the greater the flux, the lower will be the magnitude. Okay, so that is because the ancient astronomers took the brightest stars and then put them in class 1. And the second brightest they put in class 2. Right, so now, so therefore, those are called magnitudes. And as the brightness increases, the magnitude decreases. Okay, so you see that here you have got the flux there. And now, if I got two stars with flux F2 and F1, then the difference of those magnitudes, M2 minus M1, will be minus 2.5 log of F2 by F1. right? And so I can invert this equation to say F2 by F1 is 10 raised to minus 0.5 M2 by M1, M2 minus M1. And please remember that this log is with base 10. It is not the natural logarithm. The log is with base 10, right? So, so let us say that the two stars differ in magnitude by 5. And M2 minus M1, let us say, is equal to 5, positive 5. Then 5 into 0.4 is 2. So star 2 will have a flux which is 1/100th of the flux of star 1. On the other hand, if M2 minus M1 is minus 5, okay, then this will be 2, and star 2 will be 100 times brighter than the other star. Right? So now let us suppose that M2 minus M1 is small. Then you can say delta M is approximately equal to 1.086. So where does this come from? It comes from just juggling all these numbers here. I would like you to do that yourself. And delta M is equal to approximately 1 into delta F by F. Right? So delta F by F is equal to 0.9 into delta M. So if you have a difference in magnitude of 1, then you know that delta, how much is delta F by F, and so on. So typically, when the brightness goes up by a factor of 100, you've got delta M 5 magnitudes. So if one star is 5 magnitudes brighter than the other star, then you say that its flux is 100 times more. If it is 10 magnitudes, then it is 10,000 times more. So every step of 5 magnitudes gives you a factor of 100 in the flux. So now, so this is apparent flux, meaning that there can be a very bright star and there can be a faint star, but it's possible that the faint star is intrinsically brighter than the apparently bright star, but it is much further away, right? So these are called apparent magnitudes. You really don't know. This is just the observed energy. But then you've got something called absolute magnitude. And absolute magnitude, you'd like to relate absolute magnitude to the luminosity. But the way it is done is that you take any star, like the sun, and so you have got its apparent magnitude now. And then if you want to get its absolute magnitude, you must put the sun at a distance of 10 parsec. And what's a parsec? A parsec is equal to about 3.2 light years. Okay, so just please look up the definition of a parsec and see how it is connected to light year. So all stars, if you want the absolute magnitude of a star, you always put it at a distance of 10 parsec, right? The same distance. So when you put, and then you get the absolute magnitude. So if M2 and there are two stars, 1 and 2, and if M2 is less than M1, then you can say that the star 2 is more luminous than star 1. Right? That is because when you say absolute magnitude, they are both at the same distance from you. And I would like you to relate M to luminosity. That can be very easily done using the definitions which I have here. So the sun has an apparent magnitude of minus 26.7 because it is so dazzlingly bright. Okay, and so it is, but absolute magnitude of 4.83. So if you look at Sirius, then Sirius is the brightest star in the night sky. Sun is the brightest star in the sky, and the difference, you see that this distance, it has got an apparent magnitude minus 1.46. So the difference between these two magnitudes is roughly minus 25, right? So how much brighter apparently is Sirius compared to the sun? Because I told you that 25 magnitudes give a factor of 10 to the 2. So 10 to the 2, 10 to the 4, 10 to the 6, 10 to the 8, 10 to the 10. So which means that in terms of the measured flux, the sun is 10 to the 10 times brighter than Sirius. Okay, but if you look at the absolute magnitude, there's just in fact, Sirius is 3 magnitudes brighter in terms of absolute magnitude than sun. So which would mean that the Sirius emits more energy per second. It is, except that it is so far away that it appears much fainter. Right. So here, these are some of the names of the stars which are closest to the Earth. Proxima Centauri. You have heard of all this, Alpha Centauri, and so on and so forth. So you see that the magnitude range and the distance in light years. So these are all closest. The closest star is 4.2 light years, and so here you got 10.8 light years. Then you can see the distribution of stars here. So this is the sun, and then you've got all these famous stars, which are some are in the same plane as the sun, some which are outside the plane of the sun. So when you look up at the sky, it appears to you that the stars are all distributed spherically around the Earth, meaning spherically around the sun. But that is true only when you look at the closest stars. Because as you go further and further away, then you come to the disk of the galaxy, which is rather flat. We are in a flat disk. And then you can ask yourself, what is the actual density of stars in the sky? Meaning that how many stars are there? When you're talking of air, you can look at the number of molecules of air per centimeter cube. You can also do to the stars, but you'll get an unrealistically small number. So, but you say that if you take a cube with about 1 parsec of 1 parsec size, and then you'll find that there is about 1 star per parsec cube. Correct? Because you know that Proxima Centauri is just 4 light years from us. So you take a cube of with the side of 1 parsec, and there's about 1 star there. That is the density. So our galaxy is mostly empty space. And in fact, if you take into account all the protons and electrons, and then you look at and then all the gas which is there, etc., and you look at the average density of our galaxy, it turns out that there is 1 electron per centimeter cube. And compared to Avogadro's number, of course, it's very, very small. And in spite of that, the mass of the galaxy, how much is it? Take the mass of the sun, there's some 2 into 10 to the 33 grams, and there are about 10 to the 11 such things. So the mass of the galaxy is 10 to the 44 grams. Okay, 10 to the 41 kilograms. So you can see how vast is the size of the galaxy. If matter density, which is as low as 1 electron per centimeter cube, can give you so much mass. Right. So now I want to compare the sizes of stars. What are the different stars? I mean, sun is our standard. Okay, the mass of the sun is the standard mass. The radius of the sun is the standard radius. Right. So when you go to the other star, so you see that here is a range of stars, very, very, very roughly. So here you have got the sun. Then you can see as you go to smaller and smaller stars. And smaller meaning what? Are they in size or in mass? It turns out that the single most important property which determines the entire structure and evolution of the star is the mass of the star. Right? So you always talk in terms of stellar mass. So so here you can have stars which are as low as 0.08 solar masses. Just say for remembering 0.1 solar masses. Right? So that is the range of masses below the sun. And then when you go above the towards higher and higher masses, then you've got a blue supergiant here, okay, which has got a mass of about 150 solar masses. Right? So this is, you can say, is the entire range. So why don't you get stars which have lesser mass than this, 0.08 solar masses? That is because it turns out, and I'll prove that to you in a moment, is that the temperature at the center of the star is a simple function of its total mass. It's proportional to the total mass, in fact. Okay, so as the mass decreases, at some point, the temperature at the center becomes so low, temperature at the center of the object becomes so low that you can no longer have fusion. Okay, so therefore, an object of that size cannot be called a star, because a star is defined as an object which is in hydrostatic equilibrium, and then and which is producing energy at its center through nuclear fusion. So here there's no nuclear fusion, so it's no longer a star. So if you go to masses below that, first of all, you'll come to a brown dwarf, and then later on, you will go even below that, then you start coming to the giant planets, okay, like Jupiter or the giant exoplanets that we know about, right? And then when you go to the higher masses, can you get masses greater than this? Yes and no. Okay, meaning that there's something called the Eddington limit. Okay, so as you grow, as the stars become more massive, the temperature keeps increasing, and therefore you see that they appear blue in color. It's a supergiant, very large mass. If you try to go to higher masses, you see that the greater the mass, the luminosity of a star is a function of a pretty high power of the mass. You can say it goes at m to the 4, m to the 5, like that. So if you go from 1 solar mass to 100 solar masses, the luminosity has increased by a factor of L to the m to the 5, between 10 to the 2 raised to 10 to 5, between 10 to the 10. As the luminosity increases, the radiation pressure increases, and then it becomes so much at about this mass here, 100 solar masses or so, that the radiation pressure increases so much that the star will just get blown off. And that limit is known as the Eddington limit, because Arthur Eddington first worked on it. But you can go beyond this limit also, because the limit makes a simple assumption about the structure of the star. You can go beyond it. And for example, Fowler and Hall long time ago considered stars with a mass of about 1 million times the solar mass. There's nothing fundamental which is limiting it, but there's an absolute fundamental limit on how low the mass of a star can be. And then, so what are the sizes of the stars then? So here, you got between the red dwarf and our sun, you have got a little bit above that. So you got 0.1 to 10 times the radius of the sun. And here you're talking about 25 to 50 times the radius of the sun. But right at the lower side of the diagram, so there's something called a red giant, about which I'm sure you have heard. And very old stars like the sun, when will turn to red giant, the sun will eventually become a red giant, and then it has got a radius of 1,000 times the radius of the sun. Okay, but then it is not on the main sequence. It is passing through a different evolutionary stage. And how does this compare with the size of our solar system? So you see that main sequence stars, as I told you, 0.1 to 10 solar radii, and then the giants have less than 100 solar radii, red supergiants about 1,000 solar radii, blue supergiants are 25 to 50 solar radii, right? And then one moment. So the orbit of the Earth is 214 times the solar radius. Orbit of Mars is 300 times the solar radius. Orbit of Jupiter is like 1,100 times the solar radius. So when the sun becomes a red giant, it will easily cover the orbit of Mars. So we are all destined to die at that time, and whoever our counterpart then. But that's fairly much into the future, about 4.5 billion years into the future. Right. So the size of the Earth's orbit. Yeah, this is just a picture. Let me move on. So let me see here. What is the variety that you are getting? I've already given you all these numbers. One important number is what is the average density. So if you take the mass and divide it by the volume of the sun, then the density that you get is 1.4 grams per centimeter cube. Right? So that may not appear to be very impressive. Density of water is 1 gram per centimeter cube. But then you know that water is a liquid, and you know that the sun is a gas. So this is an incredibly dense gas. Okay, so then and how can you have a gas with such great density? And that is because the temperature is very high. So your surface temperature is 5,800. Luminosity, the age is about 4.5 billion years. It will have a total lifetime of about 9 billion years, and we know the distance. Right? And then how does this compare with for the stars? Please remember this table. And we will, I mean, some of these things I'll just send them to you. So it is 0.1 to 100 solar masses, 0.1 to 1,000 solar radii, and then the surface temperature can be as high as 40 40,000 Kelvin in the blue supergiants. The luminosity, I told you the luminosity goes to the high power of the mass. So which would mean that if the mass goes from 0.1 to 100 solar masses, the luminosity actually goes from 10 to the -3 to 10 to a million times the radius of the sun. So a factor of about 1,000 in the mass, okay, is giving you a factor of 10 to the 9 in the luminosity. Okay, and it turns out that the greater is the mass, the lesser is the lifetime. And why is that? Because when you've got greater mass, you can produce a lot of energy, but the energy gets produced at a very high rate. And as a result of which it evolves very fast. Right? So the most massive stars has a lifetime as short as 1 million years. And the oldest stars, I mean, you make them and then they just go on existing basically forever. Okay, greater than 10 to the 10 to 11 years. Okay, all right. So now I got about 15 minutes left. I don't want to talk for too long because you see that when it's a face-to-face talk, you get reactions of the people, and that's much nicer than here. I'm just talking blindly, right? So, all right. So now let us look at Planck's law, and I'm sure that all of you have studied Planck's law at some point or the other. And what does it say? There is something called a black body. Now, to say that how is a black body, how can the sun be considered to be a black body when it is so dazzlingly luminous? So the black body does not refer to the color of the radiation coming out. A black body, by definition, is an object in which the radiation and matter are in equilibrium. Right? So you can't have a ball of iron, but if I take, let's say, a hollow sphere of iron, okay, then the iron, and hold it at a certain temperature. Then it turns out that inside that sphere, you've got the radiation, and then that radiation and the sphere, metallic sphere, are in equilibrium. So as much energy is passing from the radiation to the sphere as from the sphere to the radiation. So the whole object remains at a fixed temperature. And then you can make a small hole in it, and then the radiation can leak out. Now, if you look at the spectrum of that radiation, then it was discovered in the 19th, towards the end of the 19th century, the last couple of decades of the 19th century. Okay, that you see that if you look at the spectrum, so you hold a sphere. Let's suppose that I had a body at 10,000 Kelvin. People didn't have such high temperatures, but I plotted here 10,000 Kelvin. But they got a plot corresponding to 2,000 Kelvin, 1,500 Kelvin, like that. So you see that you get this spectrum here. So here you got the wavelength, and here you have the intensity, meaning ergs per centimeter square per second per angstrom, and so on. And then you need all sorts of units there. And so what happens is that, so you see that here you have got the wavelength is increasing, and then you see that the intensity first keeps increasing. It peaks at a certain wavelength, okay, and then it goes down again. And if I had an object at a temperature of 5780 Kelvin, okay, so then you will find that again it peaks there, but the wavelength at which it peaks is higher than the wavelength at which the higher temperature body peaks. Okay, and then the curve corresponding to the lower temperature is completely inside the curve corresponding to the higher temperature. Now, all this was known about the black body radiation. And it was also known that if you look at this intensity here, I lambda is equal to this particular expression, this expression was also known, pretty well established, at least in parts. So here it is in the terms of wavelength, here it is in terms of frequency. So if you did it in the frequency, then here the wavelength is increasing to the right, but then you'll have the frequency increasing to the left. And the curves will maintain more or less the shape that you see here. Right, so then it turns out, what is the total energy, the flux that you get? I hold a black body at a certain temperature, and so what is the flux that I get from it, it is equal to sigma, which is Stefan's constant, times T to the 4, where the T is the absolute temperature. So what is the total luminosity that I'll get from it? So here it is not as if this is a great distance. It has got a certain radius. So per unit area, the amount of energy emitted is sigma T to the 4. And so therefore, the total energy which is emitted is sigma T to the 4 times the radius of the sphere. Okay, so which is 4 pi r square. But now there are solid angles involved, etc. But I won't go into that. So when you've got an object like the sun, you see that the sun, it has got a temperature of 5780 Kelvin. And what do you mean by temperature? Because so there, what you do is that if you look at the radiation coming from it and fit a black body to it, and that's a very incomplete way of doing things, as you'll soon discover, then what you can do is that you can, for a given star, you can take the luminosity which can be measured. Then the effective temperature is defined as if this is the temperature of a black body corresponding to the star. So L is equal to 4 pi r square sigma T to the 4. Right. So I have forgotten to include, because I just changed this diagram a little bit. I've forgotten to include an extremely important expression here, which is where does the peak occur? So it is, let us suppose that the peak occurs at a wavelength lambda, then lambda m into T is a constant. So as you increase the temperature, then the wavelength will occur at lower, the maximum will occur at lower frequencies, lower wavelengths or higher frequencies. I'll put that in the next time and I'll show you all the numerical constant. And this one here is known as the Stefan-Boltzmann law, F equal to sigma T to the 4. And oh no, I'm sorry, I got the Weins displacement law here. Sorry. So it is lambda m into T is equal to 0.29 centimeter degree. And so all this was known towards the end of the 19th century. And then, but people had no explanation for it. They could explain one side of the curve, they could explain the other side of the curve, but nobody had a beautiful explanation. Okay, and so finally, it was Max Planck who explained it by introducing the concept of the quantum. So, and you know that was a very great revolution in physics, and that happened incredibly in the year 1900. Okay, so there's a very small little book by Mukunda and tracing the history of these things. And Professor N. Mukunda is a great physicist, mathematical physicist. And then he says there that on that particular day, it was a Sunday, and Planck had gone to his friend's place for lunch. Okay, and in Europe, especially in old Europe, you called the afternoon lunch as the dinner because the most important meal of the day. So it was a family get together, and they were, I've forgotten whose house they had gone to. And then it was one of these big names that you see associated with black body radiation. And they talked about black body radiation over lunch. And then when Max Planck came home, he sat down and derived this expression that you see now. Okay, so I did introduce the concept of the quantum. So when you look at a star like the sun or like the Earth, then you say that it will look like the sun, Sirius, whichever star, you say that it's like a black body. And then looking at the color using the black body formulation, you know what the temperature. But people would have seen the spectrum of the sun many times. And then it was Newton who passed it through a prism and passed it back, and it's a white light broken up, etc. But when you actually study the spectrum, which many people did in the 19th century, and then you can see that you have got these colors here, a continuous band of colors, which is interspersed with the dark lines here. And these are known as the Fraunhofer lines. And so this is the spectrum of the star, like the solar spectrum. And then now that it was quite soon established that these lines are due to specific elements, because you can take an arc spectrum in which you get a spectrum coming for a particular element in the laboratory and then look at those lines, and then you can have different gases and so forth. And then this spectrum can be calibrated, meaning that first you need to actually measure the wavelengths of all these lines, and then you calibrate them with the standard spectra, and then you can say, my God, this is hydrogen, this is something else, this is something else. And then, for example, there are some unknown lines, and then they didn't know what those lines were, and then it was decided that those are because of a new element which is called helium, and then which was subsequently discovered on the Earth. Right, so so you see here, this is the digitized spectrum, and then actually this is the black body, this is the solar spectrum. So you see that the shape is more or less like a black body, and then this is the black body corresponding to 5780, and I've put the continuous black curve a little bit above it just so it's a visual thing, but it can be brought down. It will produce a better fit. But it is never going to be a really good fit, because the negative spikes that you see here, so these are all because of the what are called absorption lines. Okay, meaning that if you look at the mean, the energy in these lines is decreasing. So because it is dark, it means that the photons which should have been here, the black body photons which should have been here in an absorption line, have actually got absorbed. And so therefore you see darkness there. But then because these gases are hot, and then as you go to higher, more and more massive stars, when the temperature becomes higher, you will also get emission lines. Right? So, but here we are largely working in the absorption lines. So then what happens to the different stars? Stars are very faint. It's much more difficult to get the spectrum. But again, in the beginning of the 20th century, people did a very good job of that. And then they got lots and lots of spectra. So you see that each horizontal thing here is is from a different star, and these letters here they tell you that it's a star of a particular kind, meaning that this is for a star which is classified as B5, and this is for the star which is classified as M2, and so forth. Okay, so I'll soon tell you what these things mean. I mean, these are all arbitrary designations, but there's a lot of physics in the spectrum. Okay, and you can see here the lines which are mentioned: hydrogen, and then you've got magnesium suddenly coming in, helium, iron, okay, and so forth. Here you've got calcium, iron. Then there's a molecule here, actually CH, right? And then then you see that you've got TiO and so on. So there are different kinds. So in general, you can say that because you know that in order to dissociate hydrogen, you need 13.6 eV, right, to separate the electron from the proton. But then similarly, you require not so much energy, but smaller amounts of energy to strip the outer electrons in more complex elements. But if you've got a molecule, then in order to split the molecule, you require relatively low energies, and that is why these kind of the molecules occur only in the atmospheres of the lowest energy stars and at lowest temperature stars. And here I will tell you soon that this is a sequence of decreasing temperature. Right. So now you can find spectra of thousands and thousands of stars. All of these are different. In the beginning of the 20th century, the spectra was found. The spectra which are discovered, they're not so pretty like this. I mean, there used to be the spectrographs are more crude, and then you actually got them as a negative on a film. So where there are all these sharp lines, there's be blotches of things there. And there are a lot of women in Harvard College Observatory in Boston or Cambridge. Boston and Cambridge are twin cities. And then who looked at all the stars? And there are also some very inspired astronomers, and then these inspired ladies helping them. And then they set up a classification system. So what do you mean by classification system? So is that if you have, see, just like Darwin classified animals into these distinct classes. Okay, otherwise it was all living things into distinct classes, starting with the simplest and going on to and reaching us. Right, so similarly, each spectrum appears to be different, but when they looked at them very carefully, they found that one could group them together into different classes. It took a long time, a couple of decades for them to get the classes right, but the original system gradually evolved. And what you have. So here, okay, so here, sorry, you got the stellar spectra, the same spectra. So this is for F7 type star, right? So you see that then here is this in this M type star. So you can see the rough black body shape here along with the absorption lines, but you'll see that the peak occurs at a much higher temperature, much lower temperature, much higher wavelength than the peak in this yellow thing, which is actually for the sun. So it means that the effective temperature of this star is going to turn out to be 3,920. And so whereas here, this is a O type star, this is a blue star, and you see that the peak occurs in the blue region of the spectrum. Okay, and then the temperature there is 33,000 Kelvin. So this immediately tells you that by looking at the spectrum, you straight away know what is the temperature. If you just fit a black spectrum to it, a black body spectrum to it, you're going to get a crude measure of the temperature. But you can fit it with all the lines, and then you can get a much sharper measure of the temperature. So what are the meaning of the classes? So all the people who are doing the classification, they first put the, let's say, they decided that there was that there's a class called O, and you see that these are all historical. They don't mean anything at all now, but the names are stuck. So what is the characteristic of the O class? That the stars are blue in color. Their temperature is greater than about 25,000 Kelvin. Okay, and then these are singly ionized helium lines. There are some emission lines also, strong ultraviolet continuum. So these are the main characteristics of the stars. But how is the class defined? I mean, we could put any number of characteristics, but that still doesn't define the class. So what you do is that, so these classes are defined by giving an example. So an O-type star, so if you take Lacerta is a constellation. Okay, B-type star, for example, that's the 10th star in the Lacerta constellation. So B-type, the star Regan and the stars Spica. And these are all very bright stars. I'm sure that some of you have seen the stars. Okay, and the negative stars. So these are given as examples of B-type. And then it turns out that each one of these classes will be divided into 10 subclasses. So there is like a B2, A2, and then we have got examples of each subclass. So if you see a new star, what you do is that maybe people are experts at simply looking at the spectrum can say, okay, this is type A3. But for that, you require real expertise. And so, in fact, with a couple of my younger colleagues, postdocs students, we wrote a paper that we use machine learning, deep learning, actually to classify the stars. I mean, you train a deep learning network, and then you give it a new spectrum, and in just a fraction of a second, it tells you which type of star it is. So these are the spectral types, and then you've got the luminosity types. I think that each spectral type, which is mainly defined by the temperature, you can get either main stars or most luminous supergiants and so on. And so these are type 1, 2, 3, 4, 5. So there are 5 types, 2 subtypes in this class number 1. So what are the classification of the sun? So you see So the sun is G times G2, which makes it actually a dwarf star. And then you see that the luminosity class is 5. And here you got
Hello,
8.
sir.
Just
Hello. So,
and the
sorry
luminosity
to
class is
interrupt.
1.
We can
And so why the
hear.
luminosity class 1? Because it's a light. Right. So yeah, you got I don't
So we could hear certain fluctuations like in the voice.
I don't expect you to get full understand on this. You see that here on spectral time. And so if I take, for example, the K spectral time, then you can see which lines are there. You can see that there will be a lot of calcium line. Hello, yes. Oh, is that right? And I'm going to stop even now. So I'm going to stop more on this now. Let me see what happens here. Okay, let me stop here.
Hello, sir.
And
So we could hear fluctuations actually.
continue tomorrow. Because we have just spoken for an hour. Actually, I thought to break it, but there are no natural break. There are natural breaks in the second lecture. But now we have to answer questions. Can you hear me now, Prachi?
So actually we could hear a lot of fluctuations, disturbance in the voice. Am I audible?
Yes, Prachi, we can hear you.
Yeah, okay. I tried calling sir also. Ajit sir?
Prachi, your voice is pretty clear. I think it's from
Okay.
Kembhavi side.
I will try calling him on his phone.
Yeah. Maybe he can switch off the video and then just.
Yes.
Yeah, but let me just check what happened in the network. 1 moment.
Okay, I've stopped the video.
Okay, I think the power was down. Can you hear Prachi?
So the
Okay, let me
fluctuations-
try to change the network then. 1 moment.
Now it is clear.
Now is it clear now?
Yes, yes. Better,
Okay.
like better from previous.
Okay. So can you tell people that I asked them for any question? Are there any questions in the chat boxes?
Yes, there are a few questions.
Can you read out the questions, Prachi?
Yeah. Just 2 minutes. Okay, so we have a question by Pallavi Das, and she's asking that what type of filters can be used to see the flames of the sun?
Oh, what type of filter? Yeah, you see, these filters are mainly what are called narrowband filters. Okay, which means that the flames are very luminous. They can be seen in all kinds of filters. But the one I showed you, I have forgotten which filter it is, but I'll try to find out by tomorrow. But some of them are narrowband filters. Okay, you see, a filter can have a bandwidth of about 1,000 angstroms or more, but you can have the narrowband filters which have got a much smaller bandwidth, so that you are looking at specific parts of the radiation which correspond to specific lines.
So we have one more question by Dr. Sham, and he's asking that is there a drop in surface temperature of the sun in last 10 years?
As I told you, you see that if there were a significant drop, if there is any drop in the surface temperature of the sun, will be basically dead and gone. Okay? So the sun is in equilibrium. It's in hydrostatic equilibrium. It has got exactly the same size. It is emitting energy at a rather steady rate. Okay, so so you can say that there will be no such thing as a change in the surface temperature of the sun. But it is going to change, but it is going to change over a period of 10 to the 7 to 10 to the 8 years. And that also very much into the future.
So there are a lot of interesting questions. I'll just combine the two. That how do you measure the temperature as we go into the sun? Because the black body graph would give you the temperature of the surface only. And
Yes.
there is one more question about Sun, that how do you calculate its radius, by Debasmita Panda.
Ashi, first of all, the second question is much simpler. How do you know what the radius? You see, you can see the sun in the sky, and therefore you can measure its angular size. Now, using various simple astronomical things, we can measure the distance to the sun. Right? So you see, do you know the simple rule that arc is equal to linear size upon distance? Okay, meaning that if there are 2 points in the sky, and I find the angle subtended by them at my eye, that angle is the arc, and that is equal to the linear distance between the 2 points divided by the distance. So I know the distance to the sun, I know the angular size of the sun, and therefore I know the radius of the sun. Then how do we know the temperature as we go inside? You actually can't probe the sun directly. But what happens is that we can make lots of measurements on the surface of the sun, and then the theory of stars is pretty well developed. And using that theory, we can make predictions as to how the temperature should vary as you go into the sun. And there are various ways in which it can be indirectly verified because of all the solar oscillations and so on. But otherwise, it is a theoretical construct.
Okay, so we have next question, that what from Sanjay Baliwal, that what decides the star, whether it will form a binary or a single star? Like
No, there's nothing fundamental about it. It depends upon the details of the formation. It depends upon, you see, how does the star form? So there will be, when the star form, there's interstellar clouds of gas there and dust. And then if the gas in the galaxy were completely uniformly distributed, there will be no stars ever forming. What happens is that there are fluctuations in the density, right? So that you see, you can imagine that over a certain size, the density of the gas increases for whatever reason, and then it becomes gravitationally unstable. Right, so because as the density increases, the mass of that particular cloud will also increase, and then the cloud has got self-gravity, and so it slowly starts contracting. And if certain limits are crossed, then the contraction continues until the temperature at the center becomes high enough for nuclear fusion to start. Okay, and then you get a star. So now, so this is how a single star is formed. But let us say that in the stage of formation, you get 2 seeds, and instead of having the formation of a single star, we can get a formation of 2 stars which are already gravitationally bound. But then there are also other processes with which we can start. There can be 2 stars which are going, say, close to each other, and then because they form tides in each other, and the tides take energy, so that the total energy becomes negative and the stars can become bound. So there are many different ways in which you could form these binaries. Either the binaries are formed, it is like twin children being born, okay, or they can get bound afterwards.
Okay, so next question is by Mihir Kumar Tripathi, and he's asking that what are the primary difficulties faced by astronomers in determining the spectral types and the luminosity class of the stars, and what advantage do ML models provide in determining the spectral and luminosity classes?
See, the difficulty is that there's too much data. So let's say that an expert astronomer can classify maybe 10, 12, 15 stars per hour. I don't know at the rate, let's say 15 stars per hour. But then if you had the spectra of 1 million stars, how much time will it be? It will be 1 million divided by 15. That's quite a long time. Right? So then, because you get data at an extreme rate now, and in the old days, the data was available at a much smaller rate. And that is the great advantage of the ML system. So because once it is trained properly, you need a lot of expertise to do the training. But once the training is done, then the classification will be quite fast.
So next question is by Suvam Tripathi, and he's asking that how do compounds form on the surface of the stars?
All right. So you see, why are there compounds? You see what you have in our atmosphere. So you see that you don't get atomic oxygen, you don't get atomic hydrogen. They're all in molecular form. Okay. So that is because the temperature is low enough. And then there'll be lots of other compounds also in our atmosphere. So that is true also with the stars, because there are many elements present. And as the temperature goes down, okay, because you see, why do you need the temperature to go down in order to form molecules? Because as I told you, the way the binding energy of the molecule is much smaller than the binding energy of an electron to a proton. Okay, so even at lower temperatures, when the gas is in motion, the kinetic energy of the motion will be enough to actually so that something moving fast bangs into a molecule and splits it. So as the temperature increases, at a lower temperatures, you'll have complex molecules. Then as the temperature increases, the molecules of the more extended molecules will start getting dissociated. And then gradually even tightly bound molecules will also get dissociated. And then you'll only have atomic gases. And then as the temperature increases further, and then you can have a fully ionized gas.
Yeah. Okay. So the next question we have 2-3 more questions.
Yes, please.
So we have a question by Chitra, and she's asking that why the coronal region of the sun is hotter than the surface of the sun.
Yeah, so as I said, because the energy is produced at the center of the sun and then being transported outside, and then when you move upwards towards the surface, the temperature decreases. But once you cross a certain boundary, it's not a rigid boundary, but a certain distance from the sun, new processes start coming in, which are involving all the magnetic fields, etc. Okay, those new processes can generate high energy photons. And then the corona that you are seeing, and it even can go to as high as X-ray energies, right? So the corona that you see is the result of these extra processes that you get.
Okay. Okay. So the next question we have by Mridul, and he's asking that despite of having thousands of forces on the earth, and these forces, magnitude of these forces changes as the change in position in space is there. So how do day, time, and year is same?
I don't actually understand the question. And
maybe Mridul can unmute himself and ask, sir, if that is okay.
Yes, please.
Yeah. Mridul, you can unmute yourself and ask. Okay, meanwhile, we can take the next question. We have the next question by Varun, and he's asking that is the flux always calculated for visible wavelengths?
No, the flux, you see, the visible wavelengths were visible, and that was the only thing which could be seen before. But now you can have infrared detectors, you can have ultraviolet radiation. So the entire electromagnetic spectrum. So at the longest wavelengths, where the energy of the photon is the least, you've got the long wavelength radio radiation, and then you can get short wavelength radio radiation, then you get millimeter waves. And then after that, as the energy keeps increasing, you'll get to the infrared, the near infrared, and then the optical, and then you'll get the ultraviolet, and then extreme ultraviolet, and then you'll get the low energy X-rays, high energy X-rays, and then the gamma rays, and then the TeV rays. Right? So you've got the entire electromagnetic spectrum. It is just that you need more and different kinds of detectors, and the detectors were not available in the old days, but they are available now. So now we can observe virtually the entire spectrum.
So we can take the next question, that why are there, this question is asked by Preetham, and he's asking that why are there specific regions with specific energy transport mechanisms in the sun, and why is studying convection harder?
I will explain that to you a little bit in my next lecture.
Okay.
Okay. What is the meaning of convection and why studying it is harder?
Yes, it's tomorrow.
Okay. Yeah.
So yes, Mridul, you can unmute now.
Hello, am I audible?
Yes.
Sir, my question was that, like,
Mudil,
Earth.
Mudil, where are, please say where, at what level are you and where are you? Where are you studying?
Sir, I have done my graduation in IT from IABS DVV, Indore.
Okay. And what are you doing now?
Sir, I was doing currently a project with School of Physics, DVV,
Okay.
and my role was to help in IT department, like making software and simulation.
Yeah. Okay. All right. So what's your question?
Sir, my question is that, like, Earth receives several gravitation forces and everything is motion in space. So why the number of days and like timeline of a day year is same?
So, okay, let me rephrase your question like this. What you're saying is that there seem to be a lot of irregularities on the Earth, all kinds of things keep happening. It's not a smooth sphere. And so it is rotating. You know that a day has 24 hours because it rotates around its axis, right? So you see that why is it same? See, that is because, first of all, we know that it is 23 hours, 56 minutes actually. And the Earth is a very massive object. So it has got a mass of about, I think it is 1/300 times the mass of the Sun or less than that. And then yeah, there are very few forces which can actually get the body which is rotating like that. It'll have tremendous angular momentum, either to slow down or to speed up. Okay, it'll be very difficult. Number one. So everything appears to be very constant. But as your clocks develop, and then you look at it, and then you find that the motion of the Earth is not really very constant. Okay, so there are two kinds of changes which occur. There can be secular changes, okay, meaning that the Earth can gradually slow down. That is because, for example, it is losing energy to the tides. And then on the other hand, there can be violent events inside the Earth. Okay, so where there can be things like earthquakes, very massive earthquakes, all sorts of things can happen, and which get the Earth to change its time, abruptly at certain times, the rotation rate. But this rotation rate, it won't go from 24 hours to 23 hours to 22 hours. Okay, it just changes by an extremely small fraction of a second. But that can keep adding over millennia and millions of years. And therefore, you have to, in the modern times, we have to keep constantly changing, making corrections to allow for these glitches in the Earth's rotation.
Thank you, sir.
Thank you, sir, for the answer.
The next question we have by Arun, maybe we can take this as the last question.
Yes, please.
So there are two questions by him. Is it possible for a binary or a triple star system to have a common exoplanet and the planets that orbits all the stars that make up the stellar system? So I think the question is basically, is it possible for a binary or a triple star system to have a common exoplanet?
As I told you, I mean, you can ask this question later during the lecture course. But as I told you, when you've got a system of two stars, there is actually simple analytic solutions available. And you know what the shape of the orbit of the Earth around the Sun? It is an ellipse. So similarly, if you've got two bound stars, then they will both be moving in ellipses. And if one star, you see, for example, when the Sun is so much more massive than the Earth, you can say that the Sun is sitting still and the Earth is going round. But if you really want to make an accurate statement, then you'll say that there's a center of gravity for the two systems, the center of mass, you can say, and both the Sun and the Earth are in orbits around the center of mass. So now, but here there are really not just two bodies, but you know that there are other planets and so on, and so therefore they keep exerting force on the Sun and the Earth, and the orbit becomes much more complicated than just a simple ellipse. So if you've got a binary system with a planet going around it, it will be quite a complex orbit. It can be very unstable, meaning that the planet could just be chucked out of the system.
Okay. Thank you, sir. So
Yeah.
there are a few more questions, but during the course of as the course proceeds further, these questions will be answered. And if not, we are making a Google Doc of all these questions and
Yes.
see how we can share it with the participants later. Yes. Okay, thank you
All
so
right.
much, sir.
But
It was a
thank you very
interesting
much.
start.
And I got more slowly than I intended to. But so long as you understand, it doesn't matter.
Yes, thank you, sir. And we will be meeting again tomorrow, same time, 4:30. We'll start and there will be a second session by Professor Kembhavi tomorrow. Yes. See you all soon tomorrow.
Okay, bye.
Bye. Shall I end the meeting, sir?
Yes, please.